Hey guys. So previous lecture was a bit different for a couple of reasons. One is instead of using slides to back up what is being discussed, I rather wrote things with the so-called pen. I don't know how legible it was, so please pardon me if it was not that clear. And the second thing was we considered something quite new. We started off with something rather simple. We wanted to relate two different vectors. There was one caveat, rather these two different vectors, they existed in their own space. We described that space using some or by attributing some physical meaning to it. Finally, when we related it, we found that there was something emerging out of it, an entity that emerged out of it, and that entity was a bit different from our original vectors. Now, essentially, we can always represent a vector in the form of a column matrix. So the scalar components of the vectors can be represented in the form of a column matrix, and this column matrix can be written as A1, A2, A3. So this A1, it will correspond to our I, A2 will be to that of the J, and A3 will be to that of the K. So just taking the scalar components, we can write that vector as A1, A2 and A3. The same way, if this represents our A vector, we can correspondingly write our B vectors as B1, B2 and B3. So when we want to describe a vector, all that we need is just this index here. This index, one index should do the job. So I can change the index, so it means it pertains to the corresponding scalar value of that orthogonal basis. So 1i, 2j, 3k and so on and so forth. If at all, there are many orthogonal bases. So I just need one index to represent my vector. But when we were discussing, or when we were trying to bring in these two vectors of two different spaces into a single framework, we had to introduce a different entities, or we introduced rather a different entities to define which we require rather two index. So this entity involved an angle theta, and this theta, it required two index. So essentially in that way, this entity was different from that of the scalar. So we refer to this entity as tensor. Now chronologically, when we want to consider the history of the tensor, this is where things get interesting. This tensor, the context in which the tensor was introduced, people wanted to essentially relate the load, one vector, to that of the area, another vector, in a single framework. And when they wanted to relate it, they had to use this tensor, and that's the reason why this entity which requires, in this case, two index, we refer to those as tensor. And tensor, essentially it stems from the word tensile, because in the context of tensile testing, you have to relate your load to that of your area to calculate the stress. So that's the reason from the tensile testing, or this tensile testing or mathematical expression of tensile testing requires such a representation. So we had to come up with a name, or the name that was attributed to this entity was tensor. So that's how the history behind it goes. Now this we refer to it as, so when we were able to, or when we refer to these vectors based on their physical significance, we refer to this vector as load, and this vector as area, and this entity, this tensor entity, as stress. Now, of course, this appears to give us some meaning to it, or it could also be something called as a reification. In this lecture, what we want to understand is it just naming these vectors and this tensor, or do we really have some physical significance to this tensor and these vectors here? So that is one question we want to answer. Are we just introducing names to this mathematical expression and the terms involved in this expression? Are we just calling something complex as tensor? Or does it really have this tensor, which is rather characterized here by two index, does it really have any physical significance? That is one thing we want to answer in this lecture. And the second thing we want to understand is, even in this context of relating our load and area, of relating two vectors, the reason we have this two index in tensor is because we are essentially trying to relate two different frames of reference. The vector A comes with its own frame of reference, vector B comes with its own frame of reference. We are bringing it into a common space, and we are rotating it so that we are able to equate these two vectors. And that is the reason why when we are transforming our frames of reference, that is where you get these two indices entity. That is where essentially we get our tensor. So tensor essentially then plays two roles. One role is rather relating two vectors and having two index associated with it, and the other role is associated with the frames of reference. Now we want to see if this role of tensor in relating the frames of reference continue to exist, or if it does exist, if this property of a tensor relating coordinate system, does it continues to exist, or what significance does it have in our material study. So these are the two questions we want to answer. One is these names that we give, load, area, stress, in the framework of this mathematical expression, do they convey really any physical meaning? Of course, as far as the vectors go, it does convey a meaning to load, because for load we need to have both magnitude and the direction. A compressive load is exactly opposite to that of the tensile load, even though the magnitude can be the same. Now, on the other hand, area, understanding area in the form of a tensor in a vector rather might be a bit difficult, so that is something we will consider in this lecture. We will see, is it just names that we are giving, or does it hold any physical significance? That is one question we will try to answer in this lecture. The other question is, how is tensor related to that of the coordinate systems and the frames of reference? So that is the other question we want to answer. Now going to or addressing the first question, what is the physical significance of all this? Now, when you consider materials, there is a huge category, a set of materials which are rather distinguished by the arrangements of their constituting atoms. If the atoms that constitute this material are regularly arranged, we refer to those materials as crystalline materials. So when you have a category of materials wherein the atoms are regularly arranged, this entire regular arrangement of the atoms, the long range regular arrangement of the atoms, can be represented by a handful of atoms. So you have a continuum, and then you have a huge material, a macroscopic material. All through this material, the atoms are regularly arranged. If that is the case, then it is possible for us to represent this regular arrangement using a handful of atoms, and this is what we refer to as the unit cell. And what you see here is one such unit cell. So this unit cell, which just includes few atoms here, is indicative of the entire regular arrangement of the atoms. Now in this unit cell, we are focusing on one plane of our interest. So that plane is now getting highlighted. Now we are focusing on this plane of our interest. We have a unit cell that represents the arrangement of the atoms in a given crystalline material, and in that unit cell we are focusing on one plane. Now I can describe this plane by considering a vector, and my plane is rather tangential to this vector. I have a unit cell that is representative of how my atoms are arranged in a material, and in that unit cell I am focused on a specific plane. To describe this plane, I am choosing a vector. So I am saying that when I am interested in this plane which is tangential to my vector, which is parallel to my vector. So when I do that, as we saw in our previous slide, when I introduce a vector to represent my plane, I need to use one index. So let that index be I. I have a plane. I'm going to use it. I'm going to discuss with reference to that plane. So to describe it, I'm introducing a vector. My vector consumes one index. Now, within that plane, I'm going to consider different directions. So I'm going to consider one direction that is indicated in red, another direction that is indicated in green, another direction that is indicated in blue. Please give me that. So I have a plane, and in that plane, I'm considering three directions. So first, I need to have a vector to describe the plane, and that vector consumes one index. Now, in that plane, I'm going to describe three different directions. Now, to describe or distinguish each of these directions, I need to introduce, or I need to have another vector. I need to introduce another vector. So one vector to correspond to the plane, another vector to describe the direction in that plane. So I have to use two different indices. So when I use two different indices, then it becomes possible for me to talk about a specific plane and a specific direction. Now the question naturally arises, why should I have to consider a specific plane and a specific direction? Why should I have to first describe my plane and then describe my direction? Now if you look closely, imagine that you are compressing, or you are imposing rather a compressive load in the red direction, and you are comparing the response to the compressive load that is introduced in the blue direction. So this is what I am calling as blue. I don't know if it's violet or not, but still I have a red direction and the blue direction, and in both these directions I am introducing a compressive load of same magnitude. I have experiment 1 that takes care of compressive load in the red direction. I have experiment 2 which introduces compressive load of the same magnitude in the blue direction. Do you think the response will be the same? If you consider the different directions here of the same plane, because these different directions, they rather talk about different, or they rather have, or they rather describe or include atoms in different positions, the response offered, the behavior of that material in that directions will be different. The same compressive load in two different directions will behave differently. Now, if you consider a third experiment wherein you are imposing a load in the green direction, the response offered by the material in this direction is going to be different, because when I consider the direction red R, in that my atoms are in contact with one another. In blue, my atoms are just, in some places they are in contact with each other, in some places there is a significant amount of empty space. Again, in this unit cell. Now, in this unit cell, when I consider my green directions, again there is some amount of space that is present. So essentially, when I want to consider the behavior of my material, particularly in this scale, I'm able to see that depending on the plane that I'm choosing and depending on the direction that I'm choosing, the response I get, the behavior I see in my material for the same loading condition is going to vary. I'm imposing compressive load of same magnitude in red or along red, compressive load of same magnitude along blue, and the same along green. Even though the magnitude and the directions are the same of the load that I'm imposing, the behavior is going to be different because the arrangement of atoms along these directions are different, again within this unit cell. So what it essentially means is, when I'm exposing my material to a mechanical condition, the behavior that I get in response depends on both the plane and its direction. So in that case, when I want to describe the behavior of a material under a mechanical condition, under a loading condition, I need two index, one index that describes my plane, the other index that describes my direction. So this is what in our introductory session we call it as tensors. So we call tensors as an entities that require two index to be described, and in our physical system we see, particularly in crystalline material, we see that when I want to describe the behavior of the material under a mechanical loading condition, I need to talk about its direction and its plane. So I need two index. So it means for me to describe the response of my material, the behavior of a material, I need to have a tensorial representation. I will be able to understand it only, comprehensively understand it, clearly understand it only when I have a tensorial representation. So this tensor is not some sort of a reification wherein I see something, some entity, so I have to give a name to it, so I gave a name tensor. It's not like that. It has a closely knit physical significance to particularly the mechanical behavior, the tensile testing, the compressive testing, the mechanical testing of the material, because when I want to understand the load experienced by the material, the response offered by the material in the context of mechanical testing, I need to understand, I need to distinguish the plane in which I'm talking, the direction along which I'm considering. Now, it's just not for this regular arrangement, it is the same for other regular arrangements as well. So the initial one we considered, we refer to as simple cubic, this one we can refer to as body-centered cubic, and the other one, the face-centered cubic structure. In all these, the regular arrangement of atoms are observed, and depending on the plane and the directions, the response offered by the material is going to be different. Or to put it in a different way, the resistance offered by the material to your load is going to be different depending on the plane that you are considering and the direction that you are considering. When you take a material and you take a specific plane in it, and in that plane if you are considering different direction, and along the different direction if you are imposing the same amount of load, the resistance to the deformation, the resistance to the reactive behavior offered by the material depends on both the plane and the direction. This internal resistance is what we refer to as stress. So another definition of stress is the internal resistance. Apart from load by area, another definition is the internal resistance offered by the material, and this internal resistance is going to vary with respect to your area and with respect to your direction, and that's the reason why you need two indices, a tensor representation. And that is why it was rather accurate for us to refer to that tensor that related load and area as stress tensor. Because stress tensor, the internal resistance offered by the material, is going to depend on the plane, one index, direction, another index. So it's just not naming, it has a physical significance to it. Right? Now, once the tensor has been introduced, this tensor now assumes an all-inclusive understanding. What I mean by that is, when a tensor requires or demands two index for its representation, we refer to it as a second order or a second rank tensor. When a tensor, like in this case stress, it requires two indices, we refer to it as a second order or a second rank tensor. If it requires just one index, we refer to it as a first order or first rank tensor. When it requires two index, we refer to it as second order. When it requires just one index, we refer to it as a first order. And of course, when there is an entity that requires just one index, they are vectors. So what it essentially means is my vectors are equivalent to that of my first order or first rank tensors. Now what about my zeroth order tensor? So my zeroth order tensor, if you think about it, is nothing but a scalar. It doesn't require any index. So once the tensor is introduced, it becomes all encompassing, meaning you will be able to represent your vectors and your scalars as tensors. Now, of course, when you have one index, you refer to it as, so how would you differentiate a third and a second order tensor? So you call it as a dyad and you call it as a triad and so on and so forth. But nonetheless, once the tensor has been introduced, the tensor now can be used, the terminology tensor can now be used to discuss about your vectors and scalars. So the first order tensor is your vector, the zeroth order tensor is your scalar, and the third order is your triad, and so on and so forth. Right? Now, before proceeding further, having understood how the stress require both plane and direction, it is also possible, or it is also necessary rather, for us to understand the stress in terms of the load versus area. So initially when we introduced tensor, we introduced it in relation to load and area. Now we introduce stress in terms of the resistance, the internal resistance offered by the material. Now we have to go back to our original definition of the stress, that is nothing but the ratio of load by area. Now, when we want to describe the stress that is acted upon, the load that is introduced on a material in any generic direction, in order to describe it, what we essentially tend to do it, we tend to resolve it into components. So stress, it requires two index, one plane and the other direction. Now when we impose load to a material, that load is getting translated to stress because of the area that we are considering. So what we have to do is, we have to, of course, after dividing it with respect to the corresponding area, in order to ensure that we are appropriately describing the stresses or the load that is acting in the material, we resolve it into its component. So when we do that, we resolve our load that we impose onto the material that contributes to our stress into these components here. So what these components essentially do is, these components allow us to describe the load acting in any direction. So load acting in any direction, here, either individually or simultaneously, the load acting in any direction can be resolved into these components here. And as you look closely, each of these components also have two indices associated with them. So originally, when we gave meaning to the indices, we talked about the stress in terms of their internal resistance. We talked about the unit cell, and in terms of their internal resistance, we said that one of the index represents the plane, the other index represents the direction. Now we are talking macroscopically. Macroscopically, there is a need to resolve the stresses or the loads, because we are essentially considering the load that are acting in random direction. They are not acting in X, Y or Z, which we call as principal directions. They are not acting in X, Y and Z. They are acting in random directions. They could be acting individually or they could be acting simultaneously. But nonetheless, when we want to describe the load acting in random direction, we resolve them. We resolve them to a plane, we resolve them to a direction. And that's the reason when we, after resolving, we are associating the resulting stress that come out of the imposed load using two index here. Now in the first index, it represents the plane. So the first index here, Z, in these three cases represent the plane. So you have sigma ZZ, tau ZX and tau ZY. All these stresses, all these components of stresses, they are acting with reference to this plane here, to the Z plane here. The way we describe the Z plane is, this is the plane that cuts the Z axis. So all these three, they indicate, the first index of all these three indicate the plane, and the second index of all these three indicate the corresponding directions. So essentially what we are doing is, we are resolving the load acting in any directions with respect to three principal planes and three principal directions. And when we do that, we end up having 9 components of stresses, 3 indicating normal stresses and 6 indicating shear stresses. Again, we are talking about load that is imposed in random direction. It can be a single load or it can be any number of loads that are acting in random directions. In order to describe them, in order to understand them, we are resolving them into components. The way we are resolving them is, we are relating it to principal planes and the principal directions. The principal planes are x, y, z planes, x, y, z, planes, and the principal directions are again x direction, y directions and the z directions. And each of these stresses are now going to have 2 indices, one indicating the plane, the other indicating the directions. Now these that are normal to the principal plane, these are normal stresses. These stresses that are acting on the plane, these are referred to as the shear stresses. So ultimately, apart from the atomistic description, the unit cell based description, the description of stress as the internal resistance, it is also possible for us to understand that in the macroscopic scale, the stresses, they require resolution, or we resolve these stresses because they might act in any random directions. When we resolve these stresses to their principal planes and the principal directions, each of these stress components have 2 indexes associated with them. So essentially, again, we are representing in the macroscopic scale the stresses in the tensor form, and this is how we represent the stress experienced by the material. Even in the atomistic scale, in the macroscopic scale, it demands a tensor form. So with this, we will wind up the lecture, because essentially what we have seen here is, what is the physical significance of representing a stress in the tensor form? What is the real meaning associated with it, or is it just a name we are throwing at it? So that is rather the objective of this lecture. That was rather the objective of this lecture. So we will build on this in the subsequent lecture. Goodbye, guys.